we're going to take a look at some fun stuff that I got from work. Now, this is titled Needless Complication for a reason, and you'll see once I get into this. But first things first, I need to kind of explain how a refrigeration system works. So, take my amazing diagram here. And basically what we have is a compressor. And let me zoom you in a little bit here. My wonderful artwork. So we have our compressor, okay? Our refrigerant gets compressed in the compressor, comes out as a hot gas. That hot gas goes through a condenser coil, which would, in the case of a home air conditioner, be the coil that's on the outside of your house. A fan blows across that, which extracts heat from the refrigerant. It condenses that refrigerant into a high pressure liquid. That liquid gets sent into the house, into the evaporator, which is your air handling unit in the case of your home air conditioning, or the evaporator coil of a refrigerator or something like that. So then it goes through a metering device. Now the metering device can be a multitude of things. It can be an expansion valve, a thermostatic expansion valve, which is basically, I'll show you what it looks like. And it's an adjustable pin and a head that senses temperature and will allow that pin to move in and out and meter the flow of refrigerant in. Your basic setup would be a cap tube, which is basically just a tiny, really small diameter copper tube that's coiled up. Or an orifice, which is basically just a tiny hole in a metal plate. What that does is that'll take the refrigerant, the high pressure liquid, and drop it to a low pressure vapor. In other words, it'll squirt the refrigerant into the evaporator, kind of like a mist. As that refrigerant goes into the evaporator, another fan blows across it, blows the warm air from whatever conditioned space you want across it, which boils that refrigerant off. In the process of boiling that refrigerant off, it absorbs heat and turns itself into a low pressure vapor. That low pressure vapor goes back to the compressor, and the cycle starts starts the whole process over again. So basically all the refrigerant's doing is sucking heat out of the evaporator coil and transferring it to the condenser coil. That's all the refrigeration system. Any refrigeration system, air conditioning system, down to basics, that's pretty much what it does. So now in the case that's like a larger commercial system such as a walk-in, what you'll have in front of this expansion valve here, or metering device, you'll have a basically a solenoid valve. That solenoid valve will be hooked in to a temperature control. Okay, so this is usually in a walk-in cooler. Your condensing unit on the roof or outside and your evaporator coil inside electrically are not connected. So usually you'll have something like 115. Say here's a neutral. Here's power going to the temperature control and power to the solenoid valve. So basically what will happen is this temperature control will open and close this valve, stopping the flow of refrigerant or allowing the flow of refrigerant to go through this coil. Now your compressor on the outside ideally would be three-phase, so you'll have your 3 wires that'll go to a contactor, and that contactor coil will be controlled by a pressure control. So basically what will happen is your temperature control will satisfy, this valve will close, all the refrigerant will get pumped back into your condensing unit, this low pressure control will sense that, break the contactor, and your compressor will drop out and shut off. And then when this temperature control makes again, it calls for, it warms up in the box of the conditioned space, it'll turn this valve on, this valve will open, allow the flow of refrigerant back in, this pressure control will sense that and turn the compressor back on. So that's the basics thing. The reason why I show you, you'll see why I kind of show you with that. Okay, so here's the simplest of setups. Zoom me out. Whoop, zoom me out. So here is your solenoid valve. There's usually a coil on top of here. Here is your expansion valve, and this will get strapped to that suction line, and this will actually sense the temperature. This element here is full of refrigerant and has a bellows in it, and there's a pin inside that'll move up and down, which will allow more or less gas to go into the evaporator depending on temperature. Now this will never shut off completely. The only way, in other words, this is only allowed to, that pin is only allowed to move a certain amount, and the way you adjust that is with this little stem on the bottom. We'll take this apart and show you how that works. And then this here will be hooked up to a temperature control, which actually usually on the end of this there's a sensing bulb. This one broke off, which is why I had to replace it, but you see it's a temperature control here, and it just has temperature markings on that, and that is hooked in with this, and that's what controls that. So this is basically what's in a walk-in cooler at like a restaurant of some sort. Okay, so now this, just to show you what we got inside this. This is the valve body, this is the head. Now, Sporlins are replaceable heads. This body is threaded, you can take these apart. Usually Alcos, the head is actually a part of the body, especially on the smaller valves. I hate that because a lot of times what happens is these heads will rot out. So you don't have to change a whole valve, you'll just have to undo the head and put a new head on, which is great because sometimes these are so jammed into a unit. This is sweat, this is a soldered on in valve, that sometimes they're just a pain in the ass to try to get a new one in there. So sometimes you can get lucky and change just the head. So usually 3 makes of these are usually Sporlin, Alco, which I think is the same as Emerson, and the dreaded Danfoss valves, which I hate. Because they're really tiny. They have a special cartridge that sits in the side, and this cap tube, you can see how thick this is. The tube on those is like is ridiculously thin. It's like the consistency of it's not even as stiff as a it's about the diameter of a paper clip, and it's not even as stiff. So anyway, so just to show you how this works, this valve head here, depending on what the temperature is, this will expand or contract the metal plate in the bottom there, which will push up or down on these pins. This little hole is a bypass for an equalizer. You don't have to worry about that right now, but basically it pushes up and it pushes down on these 2 pins here, which in turn will push down on this plate. You can see it's a tapered pin there, point there, right inside there. This hole in the middle, that one right there, that's the seat for that pin. So this moves in and out of that pin, allowing more or less refrigerant to go through this valve. Now, what will allow you to adjust the extent of its travel is this spring on the bottom. This stem can be rotated, which puts more or less pressure on this spring, which will allow you to adjust this valve to a point. You do that to basically fine-tune a unit and get it working pretty much as efficiently as possible. They come, when you get the valves, they come relatively pre-adjusted. They're set halfway in the middle of their travel. So then once you get everything in, you can adjust it if you need to go through your superheat and subcooling adjustments and all that stuff like that, which is kind of out of the scope of this video. But anyway, so that's your basic normal, everyday, run-of-the-mill, which you'll see. Now, what we've come across in a couple places is this system called a beacon system, which basically takes this, and that, and computerizes it. What you'll have, and I wish I had kept it, is but on the side of the evaporator you have a giant circuit board, things like this big, with 3 or 4 temperature sensors, thermistors coming off of it. Those temperature sensors go to 3 spots on the coil. One hangs in the actual air off of the coil. It senses the air temp in the box or refrigerated space itself. One goes on the suction line, and one goes on the actual, usually when one goes on the inlet, right after the valve, and one goes on the outlet of the coil itself. And what all that stuff is hooked up to is that monstrosity. So basically it takes this and this and combines it into this, which is controlled by a computer, which acts as your temperature control. Now the problem I've had is there are 2 beacon systems. There's a beacon 1 and a beacon 2. Okay, so I had a beacon 1 system that completely died. The board fried. So I called up and they said, oh, we don't make that part anymore. It's beacon 2 now. You have a beacon 1 system. I'm like, okay, so give me the board for the beacon 1 system. I'll put that in. Oh, no, you can't do that. Beacon 1 system is not compatible with the beacon 2 system. You've got to be kidding me. Alright, so we just trashed that whole thing and ripped everything out and went back to a regular solenoid, expansion valve, and temperature control setup, because it was a friggin' nightmare. Even doing that, I still had to go out to the condensing unit and rewire the condenser, because a normal condensing unit will use a 208 volt coiled contactor. In the case of the beacon systems, everything is 24 volt low voltage controls going from the condenser to the evaporator, because the board controls everything. So I had to rewire and reconfigure the whole friggin' condenser, in addition with ripping apart half the evaporator. So I took this out because I wanted to see what was inside this and how this works. And what this garbage is you can see these 9,000 wires coming in the top. Here's your expansion valve. This right here is a coil. This is a magnet, and it screws in and screws out. This is a stepper motor. It's a stepper motor controlled by the circuit board. Those thermistors tell it by those sensors to either let more refrigerant into the unit, less refrigerant into the unit, or close down completely because we're satisfied on temp. So you can see there is this here. You can see how black the oil was in here, and this is not from a burnout. This black oil was inside this unit. This is like black rubbery plasticky stuff. This is from the actual coil and valve and everything. This isn't from a burnout in the system. So this valve seat right here, this is basically the same thing as that. Alright, and you can see, let's see if I can get right down through it, and there's the seat. So basically you can see it's threaded there, and what will happen is the stepper motor will, or the circuit board will tell the stepper motor to either screw in and close this down, or screw out and open it up. It's absolutely ridiculous. There is no need for this garbage at all. The only good thing about this is that this, because of the sensors, it has on-the-fly subcooling adjustment. In other words, it can adjust its subcooling right then and there, because it's actively sensing the suction pressure, the inlet pressure, and the outlet pressure, inlet temperature and outlet temperature. So it can it automatically kind of adjust the subcooling on the fly, which makes it more efficient, which is retarded. I mean, non-serviceable parts, and at least this I can, in a pinch. It's Friday at 5, 6 o'clock. I got a bad valve. At least I carry sets of heads in the truck of just I carry a medium temp and a low temp head usually. One 404 usually. A lot of times they have combo heads and stuff that are multiple refrigerants, but you carry a medium temp and a low temp head, and you can at least get them by and let them by for the weekend before you can get the part. Or if this is completely clogged inside, so sometimes these get stuck, at least I can take it apart and clean it out, because a lot of times what you get is garbage and gunk in there, and there is a screen in there, especially after burnouts and stuff, or if somebody was brazing and not using any kind of nitrogen to flow through the pipes. Sometimes, you know, either the screen can get clogged, or even I've had cases of like a waxy, pasty substance in there. It looked like flux, but it's not flux. I don't know what the hell it was, but you know, all jammed up in here. You clean it up, and at least you can get it running. This, you kind of SOL, this dies, you're kind of screwed. And like I said, if you have a Beacon 1 system that's not compatible with the Beacon 2 parts, and also nobody sells these things off the shelf. Nobody. The only parts off the shelf that I can get for those systems is the thermistor things, which is just this little sensing bulb, but no supply house is going to carry this. It's all special order garbage. So I can't even get it up and running within a day. I have to order this. So that's just garbage and ridiculous. So now another good example of just needless complication is Charleston units. Okay, Charleston units now have a keypad if you on the left-hand top corner of them, and it's all digital. Okay, and you have to have a special code to be able to enter all the programming. And if you didn't know, it's 0A. It says when you hit the set button in the middle, it's the 2 arrows. Hit the set button, it says CUS, it's asking you for a customer number. Customer number is 0A1. Type that in, that'll allow you to change the temperatures, and will allow you to check the sensors and everything. Quick tip. So that keypad is hooked into this relay box through this little idiot clip on the bottom. The clips on the side here, this one goes directly to the compressor. This goes to all the other components in the unit. You see it says a door switch, door heater, blower, line voltage, defrost. So this is from a freezer. Okay. Now what this takes the place of, in that little keypad out the front, instead of having a regular temperature control here, and especially on the freezer you need a defrost clock. Okay, it basically combines these into one digital control. So you have just a regular set of open and close contacts on this, and this here is a normal mechanical time clock. Because of a freezer, you need the freezer to go off X amount of times a day for X amount of time. These are all adjustable. What happens is your refrigeration shuts off, heaters turn on in your evaporator coil, and that melts the ice off, because the freezer is so cold. The air temp in a freezer, by health department standards, has to be 0 degrees or below. We like to keep ours at anywhere between -5 to -10, sometimes -15, depending on some applications. Some of them, we have deep freezers that need to be down to 20 below in some places. But anyway, that coil is so cold that any moisture in the air will instantly freeze to that coil. If you look at, say, your air conditioner at your house, all that water that's coming off the back is condensation and moisture it's pulling out of the air. That is allowed to come off as just condensation and drip away, because the coil doesn't usually get below freezing temperatures. A freezer coil does get below freezing temperatures, so all that moisture just creates frost on the coils. And what this does is just a timer. You have these pins here, and you can put it in these holes, and this is your actually defrost duration time. And when it hits one of these pins, get one of these out. When it hits one of these pins, it'll go into defrost, and it'll keep going for X amount of time, and then there you go, click out of defrost. And just to show you on the back, these contacts are massive. So here, you just wind it around just so you can see those contacts move. So you can see here, this one's closed, this one's open. Now this one's closed and that one's open. Now also they have, depending on the make of time clock, if this ever gets stuck, if this motor ever craps out and it's stuck into frost, you don't want those heaters on all the time. So there are safeties in the coil downstairs. Usually there's two. Usually there's a termination delay and then also a temperature, thermal protection. So the thermal protection is in line with the heaters. If it gets too hot, it just breaks the power to the heaters. That's actually a secondary to a termination switch, which basically is if that coil gets too warm, it'll send power up to this little solenoid here, which when it pulls in will immediately pop it out of the frost. And that's done off of the X terminal. A lot of times people mistakenly replace time clocks thinking that the time clock is bad because it never goes into defrost, and it's actually the termination downstairs that's bad. Usually you can take a good way to test that is what you do is if you go, what'll happen is if this is pulled in, it won't go into frost, it'll instantly click out as soon as you hit it. So it didn't even go into defrost. So what you do is just pull the X terminal off and click it around, and if that goes into defrost, then you have a bad termination switch downstairs. So a quick and easy way of not having to go up and down between the roof and the box. You can do it all from the roof. Also, another easy way to test to make sure that this is the actual clock is spinning correctly is the lowest defrost duration on this is 2 minutes. So you set it for 2 minutes, click it into defrost, and time it. There is slop in these gears, so it might not cut out, turn back on in exactly 2 minutes. But I usually give it like about 5 minutes, 5-6 minutes. If it doesn't turn back on within that amount of time, usually you can kind of be pretty sure that your dial, the motor itself, is toast. But a lot of times you can also see there'll be a little tab in there that you'll see moving back and forth. That'll tell you if the motor's actually good. But a lot of times the motor's fine. It's just this gearing in here that's all chewed up. So anyway, they took these two things that are nice and robust. I mean, you see the size of these contacts in here. They can take a decent hit. And they're rated for 2 horsepower at 208 volt and 40 amps at 208 volt. So they took all of that and put it into that keypad and this. So the keypad is basically the brains, and this is actually all the switches that control everything. Now here's what will happen. You get the call that the freezer or cooler isn't working. You go there and you open up the evaporator coil, and the thing is a block of ice, an absolute block of ice. You go and you set, you can manually set it into defrost with the keypad. You manually set the unit into defrost, and the little melty snowflake icon pops up on the display, but your compressor's still running. Well, you get the Fonzie method and go in the back of the unit and whack this. Just give it a good whack, and guess what'll happen? Unit will shut off. Well, what happens is they use, there's an idiot clip that plugs into this, which is your compressor power in and out of the compressor. They use like 16 gauge wire. They use pretty much this wire looks like this. It's roughly 16 gauge wire. Really thin in my opinion, but it's UL listed, so they get away with it. And what happens is especially from not cleaning the coil, and or a condenser fan motor dying or something along those lines, you get one of two things will happen. Well, the big thing that'll happen is this big relay inside, the contacts on this will weld itself shut. Now this thing is rated at 30 amps at Yeah, 30 amps at 277 volts, 1.5 horsepower at 120 volt, 3 horsepower at 208. And it is removable from the thing, but I don't know if you can get just these by themselves. I always get the whole control directly from Charleston. But the contacts in these will weld shut. And like I said, by whacking it, you'll kind of loosen the contacts and at least buy them some time. And the other thing is, I mean, you're pulling all that amperage through basically, let's see if I can get a decent, through these two little contact points on the board. So I've actually seen this entire thing melt. It can be completely melted. So I mean, it's just absolutely ridiculous why you would have to go through all solid state stuff to take the place of this. This is probably, I mean, I'm assuming they do this because it's cheaper, but I mean, this is way, way, way more robust. And there's no way or no easy way to convert the unit from this digital garbage to this. I have done it before because a customer went through 3 of these and it was like, you know what, just get it out. So I actually had to sit there and rewire the entire unit to use this. But I'm interested to see how robust these contacts are in there. If these things are rated at 30 amps and that's rated at 40 amps, I'm going to compare the contacts. So let me try to bust this open and see what we got inside. Alright, I tried to be as surgical as I could and we came up with some pretty good results. So here's your relay, here's your coil, and you can see that's how it pulls down when it's energized. And here's something interesting. You can see there are 2 sets of contacts and we're only using this set. And you can see how toast they are. I mean, look at that. That's completely toast. And you can see how small they are. And here's the other half that they go down to. You see, this is the front part here. Oop. Just went like that. So roughly. So I mean, even you can see how both sides are just absolutely garbage. And these are untouched, so obviously we're only using 1 set of contacts there. Now you can see this one, what did I say it was rated at? 3 horsepower at 240 volt, 30 amp at 277. This one here is this time clock here is rated 40 amp at 208 volt. Yeah, 40 amp, 208, 240, and 2 horsepower at 208 volts. So this thing is rated 3 horsepower at 240 volt, and this, let me see if I can get this in so you know I'm not lying. 2 horsepower, 208, 240. Now, three horsepower contacts. 2 horsepower contacts. See a little bit of a difference there? I mean, these are easily, you know, 2 to 3 times bigger. These are, this is rated more than this. So, I mean, I have no way to explain that. But I mean, we see a lot of this stuff around where just all kinds of digital stuff is thrown in just where it's absolutely not needed. Case in point is the newer trains. They have a most rooftop units are belt-driven blowers on them, which is just a 3-phase motor, and it's belt-driven, obviously. And you know, usually they come set up at the factory for whatever CFM that they supposedly need, but you can adjust the speed a little bit by putting new pulleys on it. But or they usually have the adjustable sheaves a little bit, so you have a little bit of a play in the speed of the blower wheel. Well, Train got the bright idea is we're going to do away with that, and what they have is a direct drive motor that's controlled through a circuit board, and there's a little potentiometer on it that will allow you to adjust the speed faster or slower. I've replaced a ton of those on the when they first came out with those. The potentiometer was like its own little circuit board. It was about this big. I've had a bunch of those die on me. The newer ones, the whole big circuit board, the potentiometer is actually built into that with a little dial. They're a little bit more robust, but I'm just dreading the day that that motor actually completely dies, because, like I said, it's direct drive, and it's driving this massive, massive blower wheel, and there's just it's just a nightmare. I mean, the units that we have that are all relatively new within the past 3 years or so. I'm just dreading the day that those die. But I mean, this is part of this is the whole, what a lot of my customers get sold on is efficiency. A lot of this stuff, especially this garbage, is sold under the guise that it's more efficient and will save you money. It won't. The price that you're going to pay in parts alone to fix it when it breaks is going to negate any efficiency or electrical savings or whatever you're going to get out of the unit. Your best bet is just, you ever hear keep it simple, stupid? You know, the simplest thing is the best way to go. And I'm all for, progression of technology and everything else like that. But I've just been seeing way too much of this stuff just be really, really shoddy and really, really not thought out. And it all works on paper, but in the real world, where you're working in a kitchen that's not necessarily the greatest of environments, where you have a lot of grease in the air, where it's really, really hot. I mean, most kitchens run, especially on coke lines, in the hundreds of degrees. I mean, it's hot in a kitchen, and you're shoving these units that are just barely up to the rating for your compressor and everything else like that. They're just gonna fail. There's no way around it. And lately, we've actually even noticed in most equipment is that most newer equipment sucks. I mean, I don't know how nice to say it, but I mean, I have some places that have walk-ins and compressors. Granted, some of them are semis, but from the 70s that are still running. I mean, we do some schools and stuff, and they had one unit that they never touched because they never had a problem with it, and the compressor is from 1978. They updated one of their units, and within the past 8 years or so, gone through 2 compressors. And we actually just looked at a rooftop unit well, the rooftop unit is junk, but the guy he needed it up and running, and it was from 1978. It was an old train, and he just needed it running. So I did what I could to get it running, but he had an original compressor in there and a compressor from 2006. The original compressor was running perfectly fine. The one from 2006 was dead. So I mean, it's just amazing at the quality of manufacturing and things that are coming out today is just nowhere near what it used to be. Granted, nothing is bulletproof, but I mean, even most of you guys know, even with your cars and stuff, they're built with the life expectancy. I mean, how many times have you had a car? Hell, I had a 1985 Chevy pickup. The thing was bulletproof. I mean, it rotted out underneath me, but the sucker still ran. And I had a 2003 Volkswagen that completely, all the electrical system screwed up on it one day. It just decided, hey, I'm not going to work, and that was the end of that. So I mean, it's just manufacturing now, especially in any kind of equipment, is just done with a life expectancy, and part of it is from the manufacturers making it so that, or I believe part of it is from the manufacturing is just to make it cheaper, and also to make it so you have to buy parts for it. Because this, I mean, I can't go down to a supply house and get this. I can't get this. I have to go directly to Charleston to get this. Or I have to go to a dealer, and that dealer is going to go directly to Charleston to get this part. This I can get from any supply house. This I can get from any supply house. This I have to go directly from Heatcraft to get. I think that's part of it too. And Train is absolutely notorious for that. I mean, they'll sell you the unit for peanuts, but man, some of their parts are just way up there, and some of them are proprietary to the units. Especially their older, not necessarily with the scroll compressors, but those older ones, the older red ones that look like a friggin' nuclear warhead. You couldn't get those anyway. You had to go to Train to get them. The newer compressors, the scrolls, by the way, if you guys are wondering, if the unit is out of warranty, look under the tag. Peel the actual tag off of the compressor, and there are actually Copeland numbers underneath that. Because the Train numbers start with an S, it's like SYS or something like that, and the Copeland numbers are usually ZR numbers. Pull the tag off, and there's actually Copeland numbers right underneath that little trick. So anyway, that's my rant on pretty much making crap complicated that doesn't need to be complicated. I mean, it makes work for me, but pisses off my customers. So hope you enjoyed this video, and we'll see you on the next one.